Good morning, good afternoon, good evening. With this lecture, I want to start the second module of the course on quantum machine learning. I'm going to start describing classical support vector machines, and later on in this module, I will discuss the quantum implementation of support vector machines. The reason why I start first with a classical machine learning algorithm is that this classical machine learning algorithm allows us to introduce some of the key features of quantum machine learning algorithms, including feature maps, variational forms of parameterized quantum circuits. And the classical support vector machine allows us to do this in a pedagogical way. Later on, in the next module, we are going to use the very same concepts and apply to neural networks. So let's give a start and look at what are a support vector machine. A support vector machine is a supervised learning algorithm. So this means that we need a dataset that has been labeled. For as classification, it can be also used for regression task. We will mainly use for classifying. In particular, we're going to focus on the binary classification, where we have two labels or two classes, and we need to understand from which dataset or which label is the data that we are analyzing. The SVM algorithm boils down to one important objective, that is find the optimal hyperplane that maximally separates different classes. And we're going to discuss what this hyperplane means. This method is quite popular in text classification, image recognition, and bioinformatics. It is one of those most important classical machine learning algorithms. So let's start with you to get a basic understanding, a basic idea of what it's about. So as I said, we are focusing on a binary classifier. So we have class 0 and class 1, and we assume that we can separate. We also assume that we have our features one-dimensional and can be separable. Because it's one-dimensional, we can put our dataset on a line. So how we can identify which one is class 0 or class 1? Well, it boils down to determine an A parameter on the line that divided class 0 data from class 1, 0. So there is one assumption that the two classes are separable, and our algorithm, the so-called training, will determine what is the A. Right? So we can design any simple algorithm, but bottom lines in 1D, we just need to determine a scalar, in this case A. We can generalize it to a 2D. In the case, we are going to have a plane, and then we are going to have a line that separates the two categories in two parts of this plane. Our classifier, in this case, or our training of the classifiers, rely on determining the line. So in 1D, we saw that we need to determine a scalar, our A. In 2D, let's say that we have two features, right, on the x-axis and the y-axis, and we assume the two classes are separable by line, then our training relies on determining the equation for these lines that separate as much as possible these two classes. From linear algebra courses, you probably remember that a line in a plane can be formulated in a vectorial form by using this equation here. So we use a vector W, right? So vector W that has a two-dimension and a scalar B as the set of points x, which is also a vector with the two components, such that the W scalar inner product x plus b is equal to 0. So this is nothing else that we can say that we can express this line using this vectorial formulation. So what is the physical meaning of the W? Well, the W is the normal or the perpendicular direction to the line, while the constant b determines the intersection of the line with the x and the y axis. By using the formulation, then we can easily tell if a point it belongs to class 0 or class 1 by taking the inner product. Any number x, which will have two components, will be on one side or the other of the line depending on the sign of the quantity of w in a product x plus b. So we have the components of the vector w, and this is given by our classifier. We take the inner product with the nx that we want to determine if it's class 0 or class 1. The inner product plus the b will tell us in which side of our plane it is. So for example, if w inner product x1 plus b and w dot x2 plus b, where x1 and x2 are 2 points, have the same sign, for instance there is x1 and x2, we will know that x1 and x2 belong to the same category. So far we talked about in the first slides about one dimension, in the second and third slides we talk about a plane. This concept can be extended to an n-dimensional Euclidean space Rn. For instance, if we have n features, we can think about an n-dimensional Euclidean space, and we can apply very much the same concepts. As we did, for instance, in a plane, in R2, we could split Rn using an n-1 dimensional hyperplane that is going to divide our hyperdimensional space in different classes. For instance, if we have a three-dimensional space, we can use an ordinary plane to divide one class to the other one. We can use the same machinery, so we can use again our w, which are physically the normal vectors to the perpendicular to the hyperplane, divided at different constant, and then some constant b in R. And then we can use the same technique. We calculate w in a product x, where x is a given point, plus b, to tell to which class our point x belonging. So our classification task is just to determine which side of the upper plane by making this inner product plus b constant. We can do some math, right? And that is generalizing. We can just rewrite this equation in the following way. I want just to summarize what are the steps. So a support vector machine, SVD, takes an input, an n-dimensional Euclidean space, and classifies them according to which side of the hyperplane they are on. The hyperplane fully defines the behavior of the support vector machine. We have an adjustable parameters that define the hyperplane, and this is the results of our training. And these adjustable parameters are the vector w and the constant b. Again, we can find these during the training. The inferior step in the SVM is to get the label of any point x, and for doing that we just check the sign of w in a product x plus b. The major assumption that we did is that the two classes can be separable, right, by a plane, a line, or a number. This is actually not true all the time. So we want to, if we want to capture sophisticated patterns, then we need to do some tricks, and we will see that these tricks takes the name of a kernel trick. This is the last slide of this lecture, and talk to you soon.